default setting is loud, so I don't usually use a microphone. This gets to be too much, let me know. Okay, and now for something completely different. I'm going to tell you about a project that is, I work at IBM in the CTO office for the cloud division, and I'm lucky enough to work on advanced technology projects, which means that I can work on things that are not currently part of our current product set, but will work their way in once we establish some proof of concept and do some sort of community acceptance or user acceptance. And so I'm going to tell you about one of those projects, and the reason that I'm telling you is because it's implemented in Lua, it uses LPEG, and there's going to be an extension language for Rosie, which will be Lua. So I have to issue a disclaimer. Does anybody else here work for a big company? More than 400,000 employees? Less than 400,000 employees? That's usually the case. So I don't speak for my employer, this is only for me. I put in this slide at lunchtime because I saw Roberta's picture of the programming in Lua book, just the spine, which is, like this big. And my first real programming experience with a real language was in Common Lisp, using a symbolic Lisp machine. And so these were the manuals for the Lisp machine. Okay, this is 1 foot. So it's 1 foot and much of another one. Anyway, that was a lot of fun. Anyone program in Common Lisp? A little bit? Yeah, it's like heroin. It's very powerful. It's very powerful, and it can ruin your life. So I switched after this to Scheme and had a 20-year love affair with Scheme. And then I met Lua. Anyway, okay, so here's the problem that I work on. In IBM's cloud division, we have a lot of different groups who process lots of unstructured data, unstructured or semi-structured. And not all of that data are like vacation pictures on Facebook and cat videos and things. A lot of it's text, and the estimates are that only 0.5% of that data is ever analyzed. And there are several reasons why, and I'm going to get to that. This is just to set the rest of the context. The group that I'm working for right now is a group that does DevOps. So you all know about DevOps. We're in San Francisco. You have to know about DevOps. It's on like every other billboard. So the group that I work for right now does DevOps analytics. So they are looking at all your Git commits and your Jira issues and your Jenkins builds, and they're mining all of that for information about how your team can do a better job building your product. And so we're doing things like predicting which files might have, are more likely to have errors in them that do not get caught in testing, and a number of other interesting things. But in any case, the DevOps Analytics platform takes data from a whole lot of different places, all the way from development through production, including business results and including business objectives. And all of this data comes in semi-structured. Some of it's JSON, some of it's text, some of it's other stuff, log files and things like that. And coming out of this analytics platform are things like anomaly detection, A/B testing analysis, predicting bugs, things like that. And so this is the domain I'm working in. And what I found is that everybody in my department who's working on this DevOps analytics platform finds themselves writing lots of regular expressions in order to extract from the incoming data just the parts that they need. This is bad. Okay, this is very bad. So here's an example of a log file. You can't read it, you don't have to read it, it doesn't matter. Log files have usually a standard format, a date and a time, and some other information. But in the middle of a log file, you can have a Java execution trace, stack trace. You can have a Python traceback. And this came from a real log file. And so what happens when you want to mine this log file for information and find out what's really going on? What happens is you spend about 80% of your time working to prepare the data to get it structured in such a way that you can then do some kind of analysis. And so we have a Spark cluster with about, I don't know, 40, 8-core machines running Spark to do analytics. And yet, in terms of the power of the people on the project, we spend most of our time, once we get some data, trying to get to the analytics part. And so a lot of the time is spent up here writing code, writing regular expressions to parse the data. And so I thought there's got to be a better way. And current approaches all seem to be based on regular expressions. So I'm going fast through the Rosie part because, so normally I tell everybody what Rosie is and how it works, and then at the very end I say, by the way, it's implemented in Lua and it uses LPEG, and here's some cool stuff about it. I'm trying in this talk to invert that relationship and go fast through Rosie, because you can read about that online and you get to the Lua LPEG part. Okay, so here's one of the quote, commonly used solutions out there called Grok. Okay, and if you know anybody that does ops, Grok is used as part of the Elastic stack, right? So ELK, those tools use Grok to parse your log files. And yeah, this is what the stuff looks like. So, who can find the bug in the IPv6 definition? Can you see where that went wrong? Yeah. So this is the problem, okay? Number one, we know that regex are basically write only. It's hard to understand an expression that you yourself wrote, let alone anybody else's work. And they're totally not maintainable, and they're not portable. So, I was writing, I guess I did a little Python coding, which uses PCRE, and somebody else was using Perl on my team, and somebody else was using Scala, which I think they were using Java's regex package underneath. And none of our expressions were portable from one to the other. So people on my own team couldn't share what they were doing, which is a problem. The second issue is really surprising. So those of us that are computer scientists probably remember learning about regular expressions in the context of deterministic finite automata and even non-deterministic finite automata. And you know that there's a linear time, linear space algorithm for matching using regular expressions. Well, surprise. Most of the implementations today don't use that algorithm. So grep is an exception. Grep runs really fast. Grep is 30 years of hand-tuned C code. That's great. But almost everything else, Perl, PCRE, Python, even SED, they use exponential backtracking algorithms, and that can really slow you down. And there are examples in the real world where this happens. This top example here is not a real world example, but the bottom one is. You've got comma-separated values. Somebody writes a regular expression to pull out the 29th field, and one line takes 65 seconds in Perl. Right? That should take microseconds. So what happens when you have a big data pipeline where you've got gigabytes of text coming in every hour, and you need to structure this data and get it into the analytics platform for analysis? You can't afford to even once or twice a day have some oddly formatted record come in and slow down your system. By the way, I put this entire presentation, I uploaded it at lunchtime to the Rosie repository on GitHub. So if you're intending to play the home game and follow along at home, you can find it there. And you might need it during this hour, during this presentation, in order to see the slides. So anyway, so the lesson really is that regular expressions are harmful at scale. If you have a lot of them, if you need to collaborate with a lot of people on them, and if your solution needs to run reliably fast. Those are three scale problems for which regular expressions seem to fail. So here's my proposed solution. The Rosie pattern language is a high-level pattern matching language that in some ways resembles regular expressions because I borrowed some familiar syntax for familiar operations. But in other ways, it completely inverts the typical regular expression paradigm. So here's what Rosie does. I'll use log files as an example because they're familiar and they're semi-structured. we take in a bunch of log records, and what Rosie spits out is for each single record, a parse tree, really. Right? So it says, okay, I matched something that is a pattern that you called syslog, and here's the text for the thing I matched. There are submatches inside syslog. There's a date time, there's an IP address, there's a process ID, and there's some other stuff. And if I look inside something like date time, I'll see that there's a date and there's a time. And if I left out some detail just so that it fits on the slides, but if I look inside the date, I can see the month and the day and the year, which is great because the date might have been in any number of dozens of formats, but if I'm really just interested in the integer values of month, day, and year, I can find them in there. And so here's what the Rosie pattern language looks like. This is RPL source code for parsing JSON, I think. Not that you would need Rosie to parse JSON, but it's a nice short example because it fits on a page. So it's designed like a programming language, and yeah, I threw this in at lunchtime too. I do want to mention that the language has closures. It's lexically scoped, and it has closures. And it has proper modules, which Lua is this close to acting. This close. So here are some features of the language. You can have comments, there are identifiers, you can put white space any place you want. Remember, this is replacing a regular expression library, right? It inverts the syntax of regular expressions. So here, if you want to match a literal string, you have to put it in quotes, right? Whereas regex, if you want to match a literal string, you just type it in, unless your string contains some characters that are considered magic, in which case you have to escape them, depending on which implementation you're using, you have to escape it differently, etc. Macros I'm going to talk about, and modules. You can see that in terms of LPEG features, so I think it was Mitchell that spoke this morning on LPEG. So in terms of LPEG features, you've got grammars, and you've got a bunch of other stuff that should look familiar. And please stop me as I go, because like I said, I'm kind of like racing towards the punchline, which is so that we can talk about how some of the stuff is built. Okay, so here's the runtime view. You've got a bunch of data coming in. It goes into a pattern engine, which is basically LPEG driven by a little skeleton piece of Lua that's just there to drive LPEG. And it's loaded up with a set of patterns, and I'll say a little bit about how they're compiled. But the output of compiling the Rosie pattern language is LPEG patterns. And so at runtime, this engine spends all of its time in the LPEG library, which actually is a great thing. And so then the output is JSON, and you can control like how deep the parse tree goes and what's inside of it and stuff. But the point is then to get that data into some other system where it'll be analyzed downstream. Okay, here's what the architecture looks like. So again, at runtime, you have an engine. You load in packages of patterns. Packages can depend on each other. I've put in the Rosie repository some common syntactic patterns. So there's maybe a couple of hundred patterns for different kinds of dates and times. Host names and IP addresses and email addresses and various kinds of things. That, on top of that base, you can then build syslog patterns and other kinds of things. And obviously, you can build anything you want. You can build stuff for parsing your sales data, if that's something you wanted to do. So this is the runtime. Then offline, there is how did you get those patterns in the first place? So you might have written them in Rosie pattern language by just firing up a text editor and writing the patterns. You might have imported them. Once I finish the importer, that converts regular expressions into Rosie patterns, right? Which is not that hard to do, it's a little subtle. There might be some domain-specific inputs. In a real live ops example, if you're running Tomcat or some other package that lets you configure your log files, well, we can just read the configuration file that you wrote to say what has to go into your log files. We can just read that and generate the Rosie pattern. And so now, from your spec of what the log file should look like, we now have a parser for your log file. And there's some other stuff going on there too. The whole thing, LPEG and Lua and the JSON library, and using CJSON, which is great. Package all this stuff up with the Rosie compiler, which is written in Lua, and a few hundred patterns. You're still left with 350 KB. Is the only footprint it takes up on disk. And it runs like 2 megabytes of memory, sort of continuously. Okay. So I wanted to get in just a really quick demo, just so you can see kind of what it looks like. I apologize if this is PowerPoint. I work in a big company. I don't know how easy it is to see this, but I'm going to try to avoid dumping a bunch of JSON to the screen. So it's also hard to type and talk into a microphone. So let me just find some file that we can use as input. And I told you that I bundled up with Rosie patterns for a couple of hundred sort of common things. I took a subset of those that are frequently found and gave them a name. And it's just a disjunction of either this thing or that thing or the other thing, and there's probably a couple of hundred built up hierarchically. And I call that that pattern basic.matchAll. And so if I run that on Etsy hosts, I get output that looks like this. When I started writing Rosie, I would give demos and it would spit out nicely formatted, organized JSON, and everyone would look at it and go, yeah, so? And so one day I decided to write a JSON to color filter, and then everyone went, wow, this is a really cool thing you have. So network addresses print in red, and random words print in yellow, and punctuation prints in black, and numbers print underscore. No IPv6. There's no IPv6 support right now. As soon as I finish the Grok importer, I'm just going to use theirs. Let's see. I'll just do one more example. Oh, wait a minute. I don't want to run this on a whole lot of files. Not that it will matter. Okay, it's running the entire system on. Yeah, there we go. In any case, hopefully you can see smudges of color from where you're setting up, which is the only important thing there. I do want to show you the REPL just quickly because we talked a little bit this morning about like how to debug patterns and things. It's really nice to have a REPL. A REPL is a wonderful thing to have. If you ask it what patterns are loaded at the moment, you get a long list. And some of these have colors defined. So if you can see red in the right-hand column. Some are definitions, some are aliases, which are essentially a very limited form of macro. And you can, of course, then match things interactively. So here's an example of the JSON output. The thing that generates the output is a Lua function that takes a Lua table as input. So you can substitute any function you want. Right now it's just set to json.encode. But you can see that common.number was matched with this string, and it happens to be a denoted hex value. So let me give it something that does not match. Okay. If the match fails, I print out a trace of everything that was tried in order to make the match work. And so it would be really nice to have a short, succinct way of conveying that information, but this is actually a pretty hard problem. So I'm experimenting with different ways. It's a long-known problem with parser combinators, which is what Rosie is implementing. Yeah, that's probably good enough. Back to slides. So in terms of implementation, the implementation right now is about 1,400 lines of Lua. I can't remember if that counts some of the like JSON to color and stuff like that, and pretty printing. But every time I add a feature, I try to do a little refactoring, so it's stayed at, even though I've been adding features, it's stayed at this size for a long time. So, you know, if you study computer science, you're going to come across combinators in lots of different contexts. They're basically just higher order functions. Parsing combinators work the same way. They're recursive, each one's a recursive descent parser. So for instance, if I look at the definition of HTTP command, it's defined as a command name followed by a URL or path. And those things, the command name, the URL, and the path, were things that were already previously defined. In fact, I've even got a package name as part of it. So it lets you build up, you know, your library of things that you can parse. If you want to read more about that stuff, you can look at the appendix, which has a lot of references. So here's some of the patterns that ship as part of the default Rosie library. And this increases every time somebody who's using Rosie inside of IBM gives me permission to post their stuff. Some patterns are really well written, and other ones could be a little bit improved, but overall the library is growing. And so, you know, from numbers and identifiers and various kinds of, you know, bracketed and quoted versions of those things, to network patterns. I've got more than a dozen ways of parsing dates and more than a dozen ways of parsing times. CSV files with 3 different kinds of delimiters, 2 different kinds of quoting methods, and 3 different kinds of escaping methods. And so, you know, you can see it's fairly easy to build up a library, because once somebody came to me and said, I use your CSV parser, but I've got data that uses single quotes instead of double quotes. That's a trivial thing to add, right? So when you have something that's working, the ability to incrementally add to it is a nice thing that is very hard to do with Regex. In terms of performance, so on the vertical scale is time, and one of the main competitors for technology like Rosie is Grok. And Grok is taking roughly 4 times the amount of time that Rosie takes for parsing the same stuff. And in fact, I wanted to continue to collect more data, but after about 2 million log entries, Grok came across a UTF-8 sequence that it thought was illegal, and so it dumped core. Which, since it's written in Ruby, I guess that was going to happen sooner or later anyway, but it was rather unceremonious. My test data for Rosie is typically a minimum of 9 million entries, because, you know, we're working on big data, and so my smallest test file is 9 million. I can only go up to 2 million in this test, but you can see it's performing well. This basically sort of wraps up with a survey of things that we don't have time to get into in any detail, but I'd be happy to talk about offline. So Rosie has lexical scope with nested environments, which means that inside the implementation, when I load in a module, I can load it in its own environment and keep it in its own environment so that it doesn't interfere with other modules or with stuff that's in the global environment. This is not exposed right now, but it will be pretty soon. So in order to expose it, I have to decide what syntax I'm going to use for import and export, and if I'm going to let you just import individual definitions or entire packages only and things like that. Macros, I've got a very simple macro facility now, which is just an alias. So an alias lets you give a pattern a different name, and so give a definition a different name, which is handy at times because you want some control over what names show up in the results, in the JSON results. One of the interesting things about macros for pattern language is that they're really just functions. Because the pattern language is already a parser, and in fact it's self-hosted. So all of the RPL that I'm typing and that I'm loading in is actually being parsed by Rosie, which was bootstrapped using an LPEG parser for a subset of the language, just enough to define the language itself. And so I've got Lua functions for manipulating ASTs already as part of how Rosie works. And so one of the questions about macros is just how to expose those. I could expose them as Lua, so we could write Lua code to then, help you write your pattern language code. I'm not sure that's the best approach. I think it needs more experimentation. There's also some work I'm doing on post-processing instructions. So one of the requirements I often get inside IBM is, in order to do analytics on this data, we need to convert the date time in whatever format it happens to be, we don't care, into the sort of uniform standard of like nanoseconds since the update. And so it's nice to be able to do that as you ingest the data, in other words, as it goes through Rosie. And a few notes about the implementation. It is self-hosting. I've got foreign function interfaces in a number of languages. Python, Perl, Ruby, JavaScript, Go. I don't really have a Lua package yet. I should probably fix that. What I did for the other languages is I put a C driver around the whole Rosie system, and using libffi, I then wrote, and this was a horrible week, by the way. I don't recommend doing this in 1 week. I wrote some Python, some Perl, some Ruby, some JavaScript, some Go, some C, and some Lua in the same week. And then I went on vacation. Yeah, some of the things I should do really, I'm working on better debugging capabilities. As I said, it's not a very well-solved problem generally. And I should also probably persist compile patterns to disk. It takes about 0.2 of a second to compile a few hundred patterns when Rosie starts up. You don't notice it interactively, and you won't notice it in the data pipeline, but it would be a nice feature to have. This way you can get all your compilers out of the way beforehand, and so that you know at runtime everything will work. So that's it. I'm very interested in some LPEG extensions to support debugging and a few other things, and so anyone who wants to chat about that later, I'm happy to do so. I know that was fast. Are there any questions?
So it seems like you chose Json as an internal representation. I was curious why you didn't just use Lua tables instead.
Oh, yeah.
That just
Yeah, so the question was about the internal representation. The internal representation is Lua tables. And so you end up returning from LPEG are Lua tables. And then I needed a text format in order to pass this down the pipeline to the next stage. And so I chose JSON, but it could be anything. Other questions?
How do you generate that debug stuff that you already have?
The trace?
Yes.
Yeah, okay. So the question is how do I generate the trace of everything that happened when the match fails? This is an LPEG enhancement that I had in mind, but that I did not do because I wanted to understand how it would work first. So when I parse the Rosie pattern language, I have an AST. When I compile it, I walk the AST and I build up a final LPEG pattern that is used for the actual matching. When the match fails, I go back and I walk this parse tree again, executing each smaller LPEG pattern that made up the parse tree until I find one that fails, or until I find the one that fails, because there's always going to be a first one that causes the whole thing to fail. And so then I show you all the steps along the way. Other questions? Yeah, in the back.
So I was just curious, if I were writing in a programming language that has parser combinator libraries, would there still be an advantage in using your language as opposed to whatever parser combinator libraries have?
That's a great question. So if you're already doing your parsing using parser combinators, like maybe in Scala or something else, what advantage would there be to using Rosie? I can think of several. They may sound sort of evangelical in nature, I'm sorry. Let's see, one of them is the language here might be better and it's more under your control than the language that you've been given through your combinator library. Another is that you can share these patterns with people who are writing in some other language that does not have the combinators, like Python or Ruby or something else. And the third is you don't need to know language semantics to write these patterns, right? And so you can write in this pattern language without knowing Lua semantics, without knowing Ruby semantics, without knowing Scala. And so if you showed me a fragment of your Scala code, I could figure out what's going on as you build up your parser. But if you use any fancy language features, or if you use a language feature that works differently than, say, the Java that I'm familiar with, I may not understand what you've read. At least this is the same. Okay. One last question?
Well, it's the same question I asked earlier of Michael, which is how much memory are you using and how do you reduce memory usage?
Yeah. So I was interested to hear. So, how many LPEG patterns do you have that you've got like 30 meg footprint in there?
100.
100. Wow. Okay, because I've got, let's say I'm loading in 200 patterns, and each pattern definition contains anywhere from 1 to a dozen or 50 LPEG patterns. So I've got more than that, but at runtime, I'm only seeing 2 megabytes of persistent paged-in memory, and about 20 megabytes total. So, like parsing all these log files and doing all the stuff that I showed you, memory usage never goes over 20 meg. I have yet to find a way to make it go over 20 meg. Yeah, we should talk later. Okay. I'm sure I'm over time, so thank you very much.